Hello everyone, this is lesson number 13, part 2. In this part we are going to go over the problems with emphasis on applying Coulomb's law in solving static charges problems. Before we start solving the problems, please make sure to watch this video over the methods by which we can charge objects and how each method affects insulators and conductors. Okay, now let's look at some problems that involve the implications of Coulomb's law. In the first example here, we have two charges that have certain distance between them r. Now what will happen if we double each charge? Now recall that Coulomb's law states that the force between any two charges is equal to a constant k times the charge of the first object times the charge of the second object divided by square the distance between their centers. So if this is the formula for case A, what would be the formula for case B? Now since the k and the distance stayed the same, the distance is still r and the constant k is still k. The only change here is in the charges. So instead of q1, we'll write it as 2q1, where q1 is the charge in case A. In case B, it will become 2q1. And the same thing applied for the second charge, 2q2. So we have 2 times 2 here, which will give you 4, while the rest of the equation represents the force in case A. Hence, when we double the charges, when we double both charges, the force will quadruple. Now notice here that the product of the two charges does not depend on the sign. The sign, whether positive or negative, will impact the direction. So if we have two positive charges or two negative charges, they will repel each other, while negative and positive will attract each other. So if those two charges were negative, we still have the same amount of force. And the direction also will be the same, because the two negative charges will repel each other. While if those two charges were unlike charges, like one of them was positive and the other one was negative, then the force will be attraction, not repulsion. So keep that in mind when you deal with Coulomb's law. Now in the second case here, we double the distance while keeping the charge the same. So what will happen to the force? Now again, if you apply Coulomb's law, so let's write the force in case A here. It will be k times, assume the charge of the first object is q1, the charge of the second object is q2, divided by the distance squared between them, r squared. Now let's compare that to the force in case B after we double the distance. K is still the same, q1 is still the same, we did not change the charges, but the distance will become, instead of r, it's 2r. And now this is the tricky part. The square is not applied on the r only, it's applied on 2r. So the whole thing here is squared, and hence the force in case B will be 2 squared in the denominator. 1/2 squared in the denominator will give you 1/4, while the numerator is still kq1 times q2 over r squared. So you can see this part here represents the force in case A, which is this one here. Hence the force in case B will be 1/4 the force in case A. Here we are asked to write the force in case A in terms of the force in case B. You can move the 1/4 to the other side or multiply both sides by 4, and this will give you 4 times F sub B. So the answer here is the force in case A is 4 times the force in case B. Make sure before we continue solving the rest of the problems that you work on them on your own, and then you can check the solution. In question number 3, we are asked about the reason gravity is not considered when we study subatomic particles. And the reason basically is because the difference between the force of electricity and the force of gravity. The force of electricity is very strong force due to the constant K. K is big value, it's 9 times 10 to the power 9 Newton meter square over Coulomb square, while the constant of gravity is very small. G is 6.67 times 10 to the negative 11 Newton meter square over kilogram square. So this is a ratio of almost 10 to the power 20. And this will make the force of gravity insignificant in the case of subatomic particles. Subatomic particles have very small mass and their charge is small as well, but the difference between the value of K and the value of G will cause the force of electricity to be much more important than the force of gravity. Question number 4 is about how a charged rubber comb will attract bits of paper and how charged balloons stick to the wall or ceiling, and we addressed that in lesson number 3 part 1 video, so I will refer you back to that video. In question number 5, why are some materials good conductors while others are not? This depends on whether the material has free electrons or not. Metals in general have free electrons, meaning their electrons, specifically valence electrons, are loosely bounded to the nucleus, and this will give the electrons the ability to move freely. While in the case of insulators, the electrons are strongly bounded to the nucleus, and hence their mobility is limited. Okay, in question number 6, we are asked about how many electrons make up 1 coulomb of charges. Now you need to know first that the charge of 1 electron, which we call it E or Q sub E, is 1.6 times 10 to the negative 19 coulomb. So this is the charge of 1 electron. The question is how many electrons will make up 1 coulomb. Now to give you an analogy to this question, if I tell you that the mass of 1 apple is equal to 0.05 kilogram, how many apples will make up 1 kilogram? Okay, pause this video for a minute and think about this question. How many apples will make up 1 kilogram? The answer is 20 apples. And you might be able to answer this question without using equations, but actually if you think about it, 1 kilogram here represents the total mass, while the 0.05 kilogram represents the individual mass of 1 apple. So the equation basically is that the total mass of anything is the number of that thing times the individual mass of that thing. So the total mass of apples will be the number of apples that we have times the mass of 1 apple. So the number of apples that will make up 1 kilogram will be the total mass divided by the mass of 1 apple. So we plug the numbers. In the numerator we have the total mass divided by the individual mass, 0.05 kilogram. And this is 0.05 kilogram per apple. And when you divide 1 by 0.05, this will give you 20. Kilogram here will cancel out with kilogram, and the answer will be apple, 20 apples. This equation here is very much the same as this equation here. The total charge, Q here represents the total charge, is equal to the number of electrons times the charge of 1 electron. So if we come here and apply the same method we did with the apple example, the total charge Q, total, of those electrons is equal the number of electrons N times the charge of 1 electron, Q sub E or E. I'll use here Q sub E. So to solve for the number of electrons, we divide the total charge, which is 1 coulomb, that's the total charge, divided by the charge of 1 electron, which is 1.6 times 10 to the negative 19 coulomb per 1 electron. And now if you carry out the calculations, as you see here, the answer will come out to be 6.25 times 10 to the power 18 electrons. This should be similar to question number 4 in the homework exercises, where you are told that an object has 1 million electrons more than protons. What is the net charge of the object? Now recall that in normal conditions, the number of electrons is equal to the number of protons. If one of them exceeded the other, the atom will become charged. So if the atom has 1 million more electrons, then its charge will be the charge of those 1 million electrons. And since we know that the charge of 1 electron is 1.6 times 10 to the negative 19 coulomb, to find the total charge, we have to multiply the charge of individual electron by the number of extra electrons. And this will give you 1.6 times 10 to the negative 13 coulomb, and this is negative charge. Okay, so let's go back to the discussion exercises. Question number 7 is application to the inverse square law that we addressed in lesson number 6, part 3. What will happen to the force when you double the distance in part A, in part B if you decrease the distance by 1/2? Whatever we do to the distance, the inverse square will happen to the force. So when you double the distance, the force will decrease by the inverse of 2 squared, which is 1/4. Hence, the force will decrease by 1/4. When you decrease the distance by 1/2, the inverse square dictates that you inverse the 1/2, which will give you 2, and then you have to square it. It's inverse, then square. So 1/2 inverse will become 2, square it, it will become 4, meaning the force will increase 4-fold. It will quadruple. Okay, on the homework questions, and again make sure first to solve it yourself. The unit of charge is Coulomb. When you have two equal positive charges that are placed equidistant on either side of another positive charge, what force would the middle positive charge experience? So you have charge in the middle, and then you have two charges that are at the same distance from the charge in the middle. This is the middle one. Now the force on the middle charge by, let's call this one number 1, by charge number 1 will be repulsion, and it will be in this direction. It's a mutual force, so this one will be repelled by the same force. And the force on the middle charge by Q2, assuming this one is Q2, will be a repulsion. It will be in the opposite direction. Now, what's the relationship between those two forces? Are they equal, or is the force by the first charge bigger, or is the force by the second charge bigger? The force by F1 will be K times Q1 times the charge of Q in the middle. Let's just call it Q middle, over R square, where R is the distance. And the force by the second object, F2, call this one F2, this is F1, will be K times Q2 times Q in the middle over R squared. Now notice here that R here is the same as R here, since they are at equidistance away from the middle charge. And we are told that Q1 is equal to Q2. Hence F1 is equal to F2, and those two forces will cancel each other. And question number 3, the physical law that describes the force between charges, that's Coulomb's law. We went over question number 4 when we answered question number 6 in the discussion. In question number 5, this is a quantitative problem where we are going to use Coulomb's law to actually evaluate the force. We are given the mass of the electron, the mass of the proton, and also we are given the distance between them. And their charges are the same. The charge of one electron is the same as the charge of one proton. The difference here is the sign. Proton is positive while electron is negative. So now if we plug those values into Coulomb's law equation, replace K by its value, which is 9 times 10 to the power 9, replace Q1 by its value, Q2 by its value, where Q1 is the charge of the electron and Q2 is the charge of the proton, divide by the distance squared between them. If you evaluate the equation here, and you might need to go back to my video over calculator exercises if you don't get this value. If you carry out the calculation correctly, you'll get 9.21 times 10 to the negative 8 Newton. And this will be force of attraction because proton is positive and electron is negative. Now, if we calculate the force of gravity between the two, and the force of gravity is always attraction, so we are using G times the mass of the proton times the mass of the electron divided by square the distance between them. This will give you much smaller value. It's 4.05 times 10 to the negative 47 Newton. So if you compare those two values, you'll find that the force of electricity is bigger than the force of gravity between the proton and the electron by a factor of 2.27 times 10 to the power 39. This is a huge difference. And that's why, as we mentioned earlier, the force of gravity is not considered when we study subatomic particles. This is the end of lesson number 13. I hope you found it educational.